This is the California desert, a place where aviation history has been written for decades. At the heart of this empty landscape lies Edwards Air Force Base.
It is one of the most important flight test locations in the world.
Inside these hangars, some of the most advanced aircraft ever built take shape. Today, engineers are preparing something truly unusual. This is the X-59, NASA's quiet supersonic aircraft.
Its nose stretches more than 11 meters, nearly a third of the aircraft's entire length.
Unlike traditional jets, the pilot cannot see forward through a normal window. Instead, the aircraft relies on an advanced external vision system.
And for 20, every surface of this aircraft has been carefully designed.
Its shape is meant to control shock waves produced at supersonic speed.
Traditional supersonic aircraft create powerful shock waves.
When those waves hit the ground, they create a sonic boom.
That boom is why supersonic flight over land has been banned for decades.
The X-59 is designed to break that boom into something far quieter.
Instead of a disruptive explosion of sound, people may only hear a gentle thump. If successful, this aircraft could change the rules of flight forever. This is the beginning of a new chapter in supersonic aviation.
As you can see, the XVS camera system replaces the forward viewport entirely.
Right, and rotating the model shows the impact on the sonic boom reduction.
Designing a quiet supersonic aircraft begins long before anything is built. Every curve and angle of the X-59 was first created in the digital world. Engineers tested thousands of shapes before selecting the final design.
The most striking feature is its unusually long and slender nose.
This shape spreads shock waves instead of concentrating them.
Normally, shock waves collide and form a powerful sonic boom. On the X-59, those waves are carefully reshaped.
Hundreds of sensors are installed to capture precise flight data.
Advanced lightweight materials help control strength and flexibility. Scale models were tested in wind tunnels across the country. These tests revealed exactly how air behaves at supersonic speed.
Every test refined the aircraft's design even further.
The aircraft's design removes the traditional forward-facing cockpit window.
Instead, cameras mounted on the nose provide the pilot's view.
This system projects a clear, real-time image directly to the pilot. Every system must work flawlessly at supersonic speeds.
Piece by piece, the aircraft comes together.
What emerges is unlike any aircraft ever built. The challenge was balancing power, efficiency, and noise.
Unlike traditional designs, the engine is mounted on top of the aircraft.
This placement helps shield engine noise from reaching the ground.
Airflow is carefully guided into the engine at supersonic speed. Exhaust noise is also shaped and controlled.
Before flight, the engine undergoes extensive ground testing.
The engine produces over 22,000 pounds of thrust.
Every parameter is monitored in real time.
Even the afterburner was tested to ensure reliability.
This was a critical milestone for the program.
The test confirmed the engine was ready for flight.
Beyond the engine, every onboard system must perform perfectly.
Advanced flight computers manage the aircraft's stability.
Thousands of hours of simulated flight came before the real thing.
Simulations help predict how the aircraft will behave in the sky.
At the heart of the X-59 is a heavily modified engine.
Testing a revolutionary aircraft requires a very special place.
Edwards Air Force Base offers miles of unrestricted airspace.
Here, NASA can safely test quiet supersonic flight.
Every bolt and system is checked again and again.
Hundreds of sensors are installed to capture precise data.
These sensors measure sound levels down to the smallest detail.
Taxi tests help engineers understand real-world behavior.
Inside the control room, every movement is analyzed.
Even before flight, critical systems are tested at speed.
The goal is not silence, but a gentle thump instead of a boom.
Originally designed for the F-18 Hornet, this engine was reworked for a new mission.
This is the difference NASA is trying to achieve.
Real people will help determine how the sound is perceived.
Human perception will guide future regulations.
Most future supersonic routes will cross populated areas.
Flights across continents could take nearly half the time.
If successful, the X-59 could change aviation forever.
This is not just a plane. It is a glimpse into the future of flight.
The external vision system is critical, as the jet has no forward window.
Even fueling and pre-flight procedures must follow strict protocols.
The modified engine is tested to ensure it produces sufficient thrust.
Taxi tests prepare the aircraft for the first real takeoff.
Pilots rely on backup visual cues and instruments if needed.
When the X-59 finally lifts off, history is being made.
For the first time, supersonic flight may occur without a disruptive boom.
NASA measures human perception to understand how the sound is experienced on the ground.
These readings will shape the rules of future supersonic travel.
By careful designing flight paths, the jet minimizes noise impact.
Regulators are using this data to reconsider supersonic restrictions.
Supersonic travel could reduce cross-country flights by nearly half.
Behind every flight is a team of engineers, scientists, and pilots.
The X-59 is not just about speed, but about redefining flight itself.
Unlike the Concorde, the X-59 could operate over land quietly.
NASA's Quiet Supersonic Jet may finally bring supersonic travel back to the skies.
After years of design and testing, the X-59 is finally complete.
Public testing marks the most important phase of the X-59 program.
Hundreds of microphones record the sound reaching the ground.
Participants are not told when the aircraft will pass overhead.
Instead of a sonic boom, only a gentle thump is heard.
Sound levels are carefully measured and analyzed.
Many people barely notice the aircraft at all.
This is exactly the reaction NASA hopes for.
Human perception is now a key factor in aviation regulation.
The difference is dramatic and measurable.
Public feedback becomes part of the engineering data.
Every system, from avionics to engines, undergoes meticulous inspection.
Engineering success is measured by how people feel.
If approved, supersonic routes over land could return.
Future aircraft may build upon the X-59's design.
Travel times across continents could be cut nearly in half.
Regulators review data before changing global rules.
A quiet revolution is taking place in the skies.
This project connects technology with human experience.
The future of supersonic flight may finally be ready for the world.